Hello there, and welcome back to the Sleep Science. You're lying there, listening to the hum of your ceiling fan when something strange begins to unfold behind your eyelids. The darkness isn't just blank anymore, it's deep, pixelated, full of strange flickers and phantom grids. You reach out and there it is, the control panel to reality itself. You, a half-sentient blanket burrito at 2:07 a.m., are now in charge of booting up an entire universe. Yep, this'll go great. You probably won't survive this. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop your city and local time in the comments. Let's see how global this little sleep cult has gotten. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You flick the switch. The lights don't come on, not because it's broken, but because light doesn't exist yet. Nothing does. No space, no time, not even darkness. You're in the conceptual lobby before the game of reality begins, hovering at the edge of everything and nothing. Your simulated universe is loading from absolute zero. Not the temperature, though it's close, but the metaphysical kind of zero, where the word before doesn't even make sense yet. The first thing your simulation needs is a starting condition. Technically, you could do this 100 ways. Maybe a simple math function, a string of binary, or something artsy like a vibrating abstract shape with far too much meaning. But let's keep it classic tonight. You decide to simulate a Big Bang, not because it's the only option, but because it's got style, an energetic flair, some nice expansion rates, and a solid review score from physicists since the 20th century. So you compress all the mass energy of your to-be universe into a single mathematical point. Not small like a marble, more like undefined. The kind of thing your physics textbook would nervously call a singularity and then immediately stop talking about. It's not really a place. It's an absence pretending to be a condition. And then boom, or rather not boom in the explosive sense, more like sudden unfolding. No sound because sound needs air and there's no air. No fireball either. That's a myth. Your universe doesn't ignite, it expands. Space itself stretches like warm dough under invisible fingers. It grows not into anything but of itself. You're watching volume happen. Temperature spikes immediately, hotter than anything you've ever seen. We're talking 1032 Kelvin. So blisteringly energetic that concepts like matter and energy haven't split apart yet. Everything is plasma soup, thick with potential. It's like alphabet soup, but the letters haven't even been invented. Time, meanwhile, clicks into existence, one Planck unit at a time, like a cosmic loading bar. Historians still argue whether before the Big Bang is a valid concept or just a philosophical trapdoor. But for the purpose of your simulation, the bang is day zero. You've hit play. Your baby universe is screaming with energy, racing outward, and already cooling faster than coffee in a metal mug. Now comes the delicate bit. You don't want everything to just radiate into nothingness. So your universe needs the right balance, a mix of chaos and containment. Here, where you start tweaking your launch parameters. A little more expansion and matter will never clump into stars. Too little and gravity pulls everything back into a premature collapse party. This is what physicists call the flatness problem, and you, lucky you, get to solve it with one slider bar. You set your expansion rate, juiced right. Goldilocks would be proud. Here's a quirky fringe tidbit. There's an actual scientific theory called the holographic principle that suggests your entire universe might just be a projection from a lower dimensional boundary. Like, literally a cosmic screensaver. Doesn't that make your job as simulator feel a bit more flattering? Anyway, right now your simulated cosmos is only a few milliseconds old, but it's already experienced more drama than the last 3 seasons of your favorite prestige TV show. Energy is converting into particles. Particles are colliding into other particles. And somewhere in this subatomic nightclub, the first matter-antimatter face-off takes place. Spoiler, matter wins by a hair. 1 part in a billion. No one knows why. Some people think it's due to tiny symmetry violations and decays. Others shrug and say maybe that's just how this one rolled. Historians still argue whether it's a fluke or a rule. That leftover sliver of matter, it becomes everything. You, this blanket, your phone, sea turtles, granola, all of it, made possible because of a petty imbalance that happened in the first blink of simulated time. You pause to check your interface. Your universe is still expanding, still cooling, and now just transparent enough to let photons travel freely. That's right. The cosmic microwave background has just been born, this fuzzy afterglow of the Big Bang that, billions of years later, some intelligent species will detect and use to measure the age of their reality. Thanks to you, by the way. For now, though, you lean back and let the simulation hum. Space is stretching, time is flowing, matter is clustering, and you're watching from the outside, sipping on imaginary coffee made of neutrino foam. The boot sequence is complete. The lights are on now, but they're not bulbs. They're photons zipping around in wild trajectories through a spacetime scaffold that didn't exist moments ago. You don't quite know where here is because you haven't programmed place yet. That's the next step. Your universe needs structure. Not buildings or galaxies, those come later, but the actual grid, the backdrop, the matrix on which reality will be painted. You're not decorating the stage, you're inventing the stage itself. You start by defining the coordinates of existence. 3 spatial dimensions feel intuitive enough: forward, back, left, right, up, down. You could add a 4th for spice, but you remember what happened last time you tried that and accidentally created an infinite donut. Not again. Let's keep it Euclidean for now. Maybe later you'll sneak in some topological mischief, just to confuse future astronomers. Now time, your 4th dimension, starts ticking in earnest. Not smooth, analog ticking like a grandfather clock, but Planck time, the shortest meaningful unit, around 10 seconds. It's the grain of the cosmic film reel. Below this threshold, even your simulation can't distinguish before from after. Everything blurs into quantum ambiguity. It's cute. Chaotic, but cute. So you've got a basic grid, 3 spatial axes and 1 ticking temporal drumbeat. But here's the weird part. That grid isn't laid out on a solid surface. There's no underlying canvas. Space is the canvas. It's not inside anything. It's more like a shape-shifting arena that stretches, curves, and wiggles in response to the matter and energy within it. Einstein called this spacetime, and he described it with equations that make your simulation engine sweat a little. But you implement them anyway. General relativity uploaded. The moment you do, the universe gets curvy. Mass warps space, energy bends time. A rogue particle zips past another and suddenly arcs, not because it's turning, but because it's moving straight in a space that isn't straight anymore. This is your first taste of geometric illusion. Light, too, obeys the bends, curling around invisible hills of gravity. Your simulation is now non-Euclidean. Congrats, you've invented cosmic parkour. You zoom in on the tiniest chunks, the pixels of existence. Are they smooth or grainy? You decide grainy. Below a certain scale, space itself becomes pixelated, voxelized if you want to get nerdy. This is the Planck length, about 1.6 x 10^3 meters. Anything smaller is just mathematical gibberish. A lot of theorists think space is quantized, not continuous, like a digital photo instead of a painting. But historians still argue whether this graininess is fundamental, or just a byproduct of our primitive modeling techniques. You don't have time to care. You're too busy tweaking the resolution of your reality. Go too high, and your simulated universe crashes from memory overload. Too low, and the physics starts to look like stop-motion claymation. You settle for a compromise that makes quantum foam look frothy but not lumpy. Now comes the connectivity. Do things next to each other know they're close? You activate locality, the rule that says objects must influence each other through neighboring interactions. No cheating with instant messages across the cosmos. But wait, should you allow some backdoor for entanglement? A little quantum weirdness. You leave the door cracked open just a smidge. Let things get spooky later. Meanwhile, you're still defining the rules of movement. You invent metrics, ways for simulated beings to measure distances, paths, durations. The speed of light becomes your built-in speed cap, not because light is special, but because that's how fast information can travel. It's your simulation's universal data limit, and it keeps causality from breaking into interpretive dance. To enforce it, you wrap your universe in Lorentz symmetry. This mathematical trick makes physics look the same no matter how fast you're moving, as long as you're not accelerating. Future physicists will lose sleep over this. They'll call it elegant. They'll also call it frustrating. You chuckle, which bends spacetime slightly. Oops. Here's a quirky nugget. In the 1960s, someone proposed that maybe spacetime isn't even fundamental. Maybe it's just a convenient emergent property from deeper entangled quantum systems, like temperature or traffic. Your universe might be pretending to have space. Think about that next time you stub your toe. The grid now pulses with energy. There are ripples in the fabric, early gravitational waves. You let them ripple freely like static on an old TV screen. They carry no information yet, but they'll someday become the whispers of cosmic events. Colliding black holes, neutron star hugs, all that melodrama. For now, they're just background noise, your universe's first ASMR track. You zoom back out. You've got a functioning lattice of space and time. It's dynamic, bendy, and subtly pixelated. Not bad for something you designed in your head under a weighted blanket. But wait, there's one more setting you haven't touched: boundary conditions. Should your universe have edges, a border, a wall you eventually bump into, you ponder the options. A closed universe curves back on itself like a sphere. Walk far enough in one direction and you'll return from the other. An open universe goes on forever, stretching into the dark unknown. A flat one hovers on the edge like a tightrope of fate. You choose a flat, infinite expansion. Because why not? It's dramatic, full of tension. Future cosmologists will debate whether your universe is truly infinite or just very, very good at pretending. They'll build telescopes, publish papers, and nod solemnly at blurry heat maps. You sip cosmic tea and smile. The scaffolding is complete. Time ticks, space stretches, and movement has meaning. Your simulation is no longer a blurry dream. It's a stage, and now it's ready for actors. Your simulation has bones now. Spacetime stretches and wiggles like a well-oiled trampoline, ready to cradle particles and cradle drama. But before you can toss in any matter or flashy phenomena, you need one crucial thing: rules. The cosmic patch notes, the governing physics engine. Right now, without them, your universe is like a video game without collision detection. Objects would drift through each other like ghosts in a badly coded indie platformer. A particle might decide to travel backward in time just to spite you. Forces would forget to force. You're trying to run a tight show here, so it's time to lay down some laws. You start with the big one, the speed limit. Everything in your universe will be capped at the speed of light, about 299,792 kilometers per second. Not because photons are special little sparkles, but because the geometry of spacetime says so. Go faster, and time starts flipping the wrong way. Distances become imaginary numbers. Suddenly, a baseball thrown fast enough turns into a time-traveling paradox grenade. So yeah, hard cap. You install it at the firmware level. Now you move on to the fundamental forces. You've got 4 main characters to cast in this sitcom: gravity, electromagnetism, and the strong and weak nuclear forces. Each comes with its own weird personality. Gravity's the moody loner. It's weak, ridiculously weak, but it works over infinite distance like a clingy ex who never stops texting. You already built it into your spacetime curvature, so gravity's handled. It just broods quietly in the background. Electromagnetism is flashier. It runs electricity, light, magnetism, everything that makes modern life zappy and visible. You turn it on, and your simulated universe gets sparkle. Particles with charge start dancing, repelling and attracting like middle schoolers at a poorly supervised dance. Then there's the strong nuclear force. This one's a bit of a musclehead. It binds quarks together into protons and neutrons, then glues those into atomic nuclei. Without it, atoms wouldn't hold, stars wouldn't burn, life wouldn't even get to fail. Interestingly, you limit its range, just a few femtometers, because otherwise everything would stick to everything and you'd have a very boring universe made of one giant proton. Lastly, the weak nuclear force. Poor weak force. Nobody really understands it. It's the backstage techie, the one responsible for beta decay and radioactive weirdness. Without it, your universe would be stuck with just hydrogen. No heavier elements, no carbon, no awkward uranium jokes. You balance the strengths and ranges of these forces with care. Too strong and matter clumps into weird neutron goop. Too weak and it all floats apart, lonely and unresolved. You tweak the coupling constants just slightly, an epsilon here, a decimal there. Future physicists will call them fine-tuned. They'll write entire papers about how unlikely it is that your universe can support life. You'll sip coffee and say, "Yeah, I did that." Historians still argue whether these constants are truly arbitrary or if some deeper theory, like string theory or loop quantum gravity, is hiding behind the curtain, holding a cheat sheet. You leave it ambiguous. A good simulation always has secrets. Next, conservation laws. These are your universe's security guards, the rules that say you can't just create or destroy stuff for fun. Energy is conserved. So is momentum. Angular momentum, too, because you want your spinning planets to stay stylish. You enforce these laws using symmetry principles. Emmy Noether figured this out back in the early 20th century. Every conservation law comes from a symmetry. Time symmetry gives you energy conservation. Space symmetry gives you momentum conservation. It's elegant. It's powerful. You add it with a toggle switch labeled Noether's fabulous math hack. Here's a quirky twist. There's a debate about whether the constants of physics could change over time. Like, what if the fine structure constant drifted slightly over billions of years? Some telescopic data even hinted at it. But your simulation is clean, unless you decide to spice it up later, of course. You also program in uncertainty, because what's a universe without a little chaos? You implement Heisenberg's uncertainty principle. A particle's position and momentum can't both be precisely known. It's not that the data is hidden. It doesn't exist until measured. Your simulation now has built-in mystery. You can thank quantum mechanics for that, probably the most misquoted branch of science in all of YouTube history. You code in wave-particle duality while you're at it. Photons are both waves and particles, so are electrons. It's like your universe can't make up its mind. Light behaves like a ripple until you look at it, and then it acts like a marble because it feels watched. Very relatable. Oh, and entanglement. Absolutely, you bake it in. Two particles born from the same event can be separated by light years and still behave like they're reading each other's text messages. No one really knows how it works. Einstein hated it, called it spooky action at a distance. You smile and label the function SPOOKYMODE equals true. At this point, your laws of physics are up and running. They're mathematically clean, a little strange, and more importantly, predictable. You don't want too much weirdness. You want a universe where chemistry is possible, where cause still mostly leads to effect, and where reality doesn't trip over its own shoelaces. But you also leave room for bugs. Little asymmetries, a barely off-center distribution of matter, a slightly skewed expansion rate. These imperfections are the seeds of structure. Galaxies, stars, planets. Without flaws, your universe would be an undifferentiated cloud of boredom. Your physics patch notes are complete. You read them back like a changelog. Added causality stable. Enabled spacetime stretchy. Implemented 4 forces, balanced-ish. Activated quantum uncertainty, flickery. Capped speed at light limit, fast enough. Bugs intentional. You lean back satisfied. Somewhere in your code, the first quantum fields begin to hum. They're not particles yet, not until something disturbs them, but the rules are ready. Now all you need are players. Your simulation's grid is humming, the physics engine's purring like a cosmic cat, and the laws of reality are neatly stitched into every voxel of space. But so far, it's all a bit sterile, like you've built the world's most advanced sandbox and forgotten to put in any sand. That changes now. It's time to select your universe's building blocks: matter, particles, stuff. You start small, unimaginably small. You could begin with atoms, but no, those are way too mature for this stage. You need to sculpt your universe from the subatomic up. So you crack open the standard model particle menu, and it stares back at you like a character select screen in a weirdly technical fighting game. Your first pick, quarks. These jittery little gremlins come in 6 flavors: up, down, charm, strange, top, and bottom. Yes, those are the real names. Physicists were clearly sleep-deprived when they named them, but that's fine. You mostly need the up and down ones. Combine 2 ups and a down and you've got yourself a proton. Flip the ratio, you've got a neutron. The rest are rare, high-energy snacks, perfect for those brief, dramatic moments in your simulated particle accelerator levels. You release them into the quantum fields like sprinkling seeds on a tilled garden. They pop into existence, immediately swarming and swirling, held together by the strong nuclear force. Each quark comes with a color charge: red, green, or blue. No, not actual colors, but metaphorical ones. Still, they have to form color-neutral combos like a cosmic RGB balance system. It's nature's way of saying, yes, even quantum mechanics has aesthetic rules. Next, you spawn the leptons. These are your light, independent types. Electrons are the divas, always flitting about, refusing to stick with anyone unless they're in a well-defined orbital relationship. You also include neutrinos, little ghost particles that barely interact with anything. They're like the introverts of your universe. They're there, but they really hope no one notices. And of course, you add the antiparticles. Each matter particle gets a mirror twin with opposite charge: anti-electrons, antiprotons, antiquarks. When matter and antimatter meet, they annihilate into pure energy. It's dramatic, it's final, it's extremely tidy. But remember back in Section 1 when matter eked out a narrow win over antimatter in the first microseconds. This is why your simulation isn't just a bright flash followed by eternal nothing. Historians still argue whether that asymmetry is baked into the laws or a freak statistical fluke. You don't clarify. You like keeping your players on their epistemological toes. You zoom out slightly. All across your simulation, tiny clouds of energy are fizzing into particles. Some form stable families. Protons and neutrons begin to buddy up, locked together by the strong force into nuclei. It's still too hot for electrons to join the party. They're out there, sulking, waiting for the universe to chill a bit. Here's a fun fringe thought. Some researchers think the building blocks of reality might not be particles at all. Maybe everything is just vibrating strings, tiny one-dimensional loops resonating at different frequencies. Change the vibration, change the particle. It's elegant, weird, and mathematically unforgiving. You toggle string theory, experimental in your backend menu, and quietly ignore the warnings. Anyway, back to your simulated reality. Once you've got protons and neutrons snuggling up in atomic nuclei, you let the universe cool just enough for electrons to swoop in. They don't crash into the nuclei, they orbit, held in place by electromagnetism, zipping around in probability clouds you can't quite pinpoint. Now you've got hydrogen, lots and lots of hydrogen. A few helium nuclei too, and trace amounts of lithium, not much else yet. Heavier elements need stars to forge them, and your universe is still a big, dark cloud of potential. Everything's still floating. No planets, no galaxies, just a sea of light atoms drifting through expanding spacetime like confused soap bubbles. But you've laid the foundation. Your particles are stable. They obey your laws. They combine in ways that are predictable, repeatable, and surprisingly beautiful. And the ratios matter. A slight tweak in the neutron-to-proton balance, and your whole universe evolves differently. No stars, no carbon, no cozy bedtime stories. But you've got it just right. Future chemists will marvel at the elegance of the periodic table, not realizing you sculpted it with sleepy fingers and a stubborn insistence that oxygen definitely deserves a starring role. You check your simulation's readouts. Density, uniform but with slight imperfections, your coded quirks from earlier. Temperature, dropping steadily. Particle interactions, normal. Everything is proceeding with that quietly alarming inevitability that suggests you're doing something very, very important. Here's your quirky fact of the night. In 2012, a team of researchers simulated a single atomic nucleus, carbon-12, using a lattice model that broke spacetime into a discrete grid. It took months of supercomputing power to simulate something you just built in a lazy Tuesday minute. You smirk and stretch your arms across the pillow dimension. Soon, these tiny atoms will start clumping. But right now, they're drifting, barely noticing each other, like awkward commuters on the first day of a long, long cosmic journey. And somewhere, deep in the cold of expanding space, one photon finally breaks free of the particle soup and begins its lonely trip across the void. It will travel for billions of years, bouncing off nothing, passing star after star, until one night, a simulated creature on a tiny blue planet points a radio dish at the sky and catches it, decoding the whisper of your universe's infancy. That whisper, it started with quarks. Now that your simulation is fully stocked with quarks, electrons, and the occasional camera-shy neutrino, things are starting to feel a bit less like raw code and more like a universe. But so far, everything is just floating, gently, aimlessly. Your particles are following the rules, they obey conservation laws, keep their charges balanced, and drift politely in the expanding soup. But they're lonely, isolated, still too scattered to get anything juicy started. That's when you decide to activate the universe's most introverted extrovert, gravity. Gravity's already been lurking in the background, coded into the very curvature of spacetime. But now, it finally gets to do something. Like a party guest who's been watching from the sidelines and is suddenly handed the aux cord. You know how this goes. Mass tells space how to curve, and space tells mass how to move. That's the beautiful summary attributed to John Wheeler, who managed to explain general relativity like a bedtime poem. You're not adding a force so much as letting geometry take control. Particles don't pull on each other directly. They fall toward the lowest spots in the spacetime mattress you've stretched beneath them. It's subtle at first. Hydrogen atoms here and there start drifting infinitesimally closer. Helium clouds gently slosh toward regions of ever so slightly higher density. The imperfections you built in earlier, those slight over and under densities, are finally earning their keep. Without them, gravity would have nothing to do. Everything would stay perfectly spread forever. Boring. But thanks to your tweaks, the universe has texture, and gravity loves texture. So it begins. Tiny clumps attract more matter, clumps grow. Regions of higher density start pulling harder. It's a cosmic popularity contest. The more mass something has, the more it attracts, and the more it attracts, the more mass it gains. Feedback loop achieved. Eventually, your universe will be riddled with structure, clusters, filaments, voids. But right now, you're watching the very first hints of that dance. Historians still argue whether gravity is fundamental or emergent. There's a camp that believes it might actually be the thermodynamic behavior of information across a surface, essentially, a side effect of entropy. That's like saying gravity is an illusion caused by the way information organizes itself. You don't weigh in on the debate. You're too busy watching dust clouds do synchronized swimming routines across millions of light years. You pause to adjust a tiny parameter, the gravitational constant. It's a small number and it has to be just right. Turn it up too high and everything collapses too quickly. Black holes form before chemistry can even throw a party. Turn it down too low and matter never clumps at all. You fine-tune it like a DJ balancing bass levels. A Goldilocks tweak. Again. Now here where things get funky. Gravity works on everything with mass or energy. That means even photons, massless little speedsters, feel its pull. Not by slowing down, of course, but by bending their paths through curved space. You set up a quick test, spawn a beam of light near a massive clump of gas. Sure enough, the path curves gracefully around the region like it's orbiting something invisible. Congratulations, you've just observed gravitational lensing. Later, simulated astrophysicists will discover this effect and use it to detect galaxies hidden behind other galaxies. You're already proud of them. You decide to run a quick time skip, a few 100 million simulated years, just enough to let gravity have some fun. The results are beautiful. Across your universe, massive filaments of gas are starting to coalesce. Voids form between them, enormous stretches of nearly nothing. These cosmic structures resemble a sponge or maybe a neural network, or perhaps a mildly overcooked waffle. Whatever you see in it, it's haunting and mathematically gorgeous. A quick historical aside, the cosmic web, this sponge-like large-scale structure, wasn't even fully confirmed until the late 20th century. Simulated humans had to build sky surveys, radio telescopes, and some seriously overworked CPUs just to map what you're casually rendering in your sleepwear. Your clumps are becoming denser. In their centers, pressure mounts. Gravity crushes gas into tighter and tighter balls. Temperatures spike. You know what's coming next, but you don't rush it. The show is better when it simmers. And all the while, gravity keeps connecting things. Not instantly, nothing is allowed to cheat the speed of light, but inevitably. The interconnectedness of the universe becomes more apparent with every passing megayear. Galaxies will form from these clumps. Stars will ignite. Planets will spin. None of that is possible without this slow, tireless pull toward the center. Here's a fun, fringe thought before we move on. In 2018, a theoretical physicist proposed that gravity might be an artifact of quantum entanglement across the boundaries of spacetime. Essentially, that what feels like gravity could be the manifestation of quantum information rebalancing itself. Yeah, you don't code that in yet, but you keep it in your back pocket. Back to your simulation. You check in on one particularly enthusiastic region. Let's call it Sector 1987C. There, a swirling pocket of hydrogen is collapsing fast, faster than most. The density is off the charts. You watch the gravitational well deepen until nothing, not even light, can escape. And just like that, you've got your first black hole. It's a bit premature, honestly. This one probably formed from direct collapse of gas, not from a star's death. But it works. You leave it. Future physicists will puzzle over it and call it a seed black hole. They'll wonder if these are how supermassive black holes got their start. Historians still argue whether those seeds formed from early stars or just happened. It's weird, it's fascinating, it's yours. And so gravity, your quiet, invisible puppeteer, continues. Tugging, shaping, orchestrating the slow descent of matter into elegance. Every dust particle, every atom, every photon bent subtly by the underlying dance of spacetime. What started as floating particles is now a growing cosmic network. You lean back, listening to the gentle hum of your universe knitting itself together under the soft, constant pull of its own weight. Your universe is collapsing in all the right places. Gravity has done its job. Tidy clouds of hydrogen and helium have started spinning, pulling themselves into tight knots. Pressures build, temperatures soar, and in the dense hearts of these proto-structures, something new happens. Something truly spectacular. Something hot. You watch as the centers of these gas clouds ignite, not with fire but with fusion. A delicate dance where hydrogen atoms start smashing together, forming helium and releasing energy in the process. Lots of energy. Your first stars are born and they are dramatic. Noisy, luminous, unstable things, like toddlers with flamethrowers. This is the moment your universe becomes visible. Before this, it was like wandering around in a fog bank made of microwaves. But now light has a source. Not just the scattered background hiss of the early plasma, but sharp, bright beams piercing the cosmic night. Your stars blaze in every color, mostly in the ultraviolet because they're massive and young and have no chill. They're mostly made of hydrogen because that's all you really gave them to work with. A few helium atoms here and there. No metals yet. Astronomers will one day call these the population III stars, the OGs, the pioneers. The ones nobody's ever directly seen because they lived fast, burned hard, and died young. But you're watching them party in real time. They don't last long. A few million years, maybe. Their cores churn through hydrogen at absurd rates, fusing elements up the periodic table. Helium, carbon, oxygen, onward to iron. And then bam, a spectacular death. The core collapses, outer layers rebound, and just like that, the first supernovae light up your universe like cosmic paparazzi. With those explosions, you finally start getting some variety. Supernovae are nature's way of distributing the good stuff: carbon, nitrogen, silicon, iron, gold. You sprinkle these heavier elements into the surrounding gas, seeding future generations of stars and planets. The cosmic recycling program has begun. Historians still argue whether some of these first stars went directly into black holes without even a supernova. You don't tell them the answer. What's the fun in that? As more and more stars pop into existence, your universe becomes a glittering sea of light. But the light doesn't travel forever, not yet. The space between stars is still thick with neutral hydrogen, which absorbs those energetic photons like a sponge. You've entered the cosmic dark ages, but now the light is winning. You initiate cosmic reionization, a slow, radiant transformation. Over hundreds of millions of years, ultraviolet radiation from young stars strips electrons off hydrogen atoms across vast stretches of space. Bit by bit, the fog clears. Photons can travel freely. Your universe goes from opaque to transparent, like opening the curtains in a dark room after a very long nap. Somewhere in that newly illuminated void, light bounces off a cluster of collapsing matter and bends. Not because it's doing tricks, but because of gravitational lensing, your earlier handiwork. It's a subtle distortion, but it will let future civilizations map galaxies billions of light years away. Your simulation isn't just growing, it's becoming observable. Let's talk about light for a moment. You programmed it to move at a fixed speed, the maximum speed in your universe, but that doesn't mean it's simple. Photons are weird. They have no mass, but they carry energy. They don't experience time. From a photon's perspective, the moment it's emitted and the moment it's absorbed are the same. It never travels. It just is in two places, linked by the sheer weirdness of quantum electrodynamics. You glance at your simulation console. The first galaxies are beginning to form, spiral arms swirling like cosmic cinnamon buns. Light from their stars paints your universe in warm hues: reds, oranges, silvers. The voids between them are deep and dark, but the stars are like punctuation, declarations of something working, something beautiful. Here's a quirky, fringe tidbit. Some researchers once speculated that light might tire over distance, that redshift wasn't due to expansion, but exhaustion. This tired light theory was eventually shelved, but you smile at the idea. It would be so human for the universe to age by simply getting tired of shining. Instead, you gave it expansion. So as light travels, it stretches, wavelengths grow longer, colors shift toward red. That's redshift, and it tells anyone watching how fast something receding. Your entire simulation is communicating subtly through this silent stretching of light. The galaxies aren't running away. The space between them is growing, which somehow is even lonelier. Zooming in on one particularly lively patch, you see a young star cluster erupting with radiation. Gas around it glows pink and violet, the hallmark of hydrogen recombination. And just beyond that, a supermassive black hole is forming in the center of a swirling proto-galaxy. Its gravity bends light in wild ways. The surrounding disk spins near light speed. This thing could devour suns. You quietly name it Steve. Meanwhile, billions of photons race across your simulation. Some will hit comets, others will never touch a thing. A lucky few will strike the retinas of intelligent creatures who will look up at night and say, I wonder. That's your light, your stars, your fusion-powered glitter bombs. You notice something lovely. The heavier elements forged in those first supernovae are already drifting into new gas clouds. The next generation of stars, population II, will burn longer, cooler, more stable, more planet-friendly. That's important because soon you'll need a good stage for chemistry, and chemistry needs elements beyond hydrogen and helium. You need carbon, oxygen, phosphorus. You need the ingredients for DNA, volcanoes, peanut butter. You need complexity, and complexity only blooms under the steady light of stars. But tonight, you let the first lights shine. Your simulation is full of points, tiny, twinkling declarations that energy has finally found a rhythm. You lie back in the darkness, watching light move through space for the very first time. And like any good simulator, you bask in the quiet glow of your own creation. Time has been ticking ever since you pressed play on your cosmic sandbox, but only now do you realize what a strange, slippery creature you've let into the simulation. Time isn't just a background rhythm, it's part of the machinery. Without it, there'd be no change, no evolution, no fusion or galaxies, or you lying here wrapped in a blanket watching your pretend universe get weirder by the second. But let's be clear, time isn't simple. You gave your simulation a fourth dimension, tethered to the fabric of space. But unlike the X, Y, and Z axes, time insists on flowing. It has a direction. You move forward in it, not backward, and there's no sideways either. This forward-only march is called the arrow of time, and it emerges from a single, stubborn rule: entropy increases. We'll get to entropy in all its chaotic glory later. But for now, know this. Your universe has a sense of progression because it started in a state of incredibly low entropy, and it's been climbing ever since. That's what makes eggs break, stars burn out, and people age. It's not because clocks say so. It's because your simulation is always moving from order to disorder, like a slowly crumbling sandcastle. You tweak the internal engine to respect that flow. One tick after the next, events happen then cannot unhappen. There's no rewind button, but here, where things start to warp. Because time, in your simulation, isn't universal. That clock you coded, it lies depending on who's reading it. You built in relativity, remember. That means every observer experiences time a little differently depending on their speed and location in a gravitational field. If someone's near a black hole, their clock slows down. Not broken, just stretched. A year near the event horizon might be 1,000 years to someone far away. If something moves near light speed, time squashes flat for them. Distance contracts. Everything gets weird and melty, like a Dali painting rendered in Planck units. Historians still argue whether time is a fundamental property or just an emergent one. Maybe it's not real in the way we imagine. Some physicists propose that it's just our brains making sense of causally related events. You don't rule that out. You built time as a bookkeeping trick, a very convincing one. Meanwhile, your simulation is already several 100 million years old, give or take a few 100 million. Time flows smoothly across most of the grid, but when you zoom in on dense, dynamic places, like galactic centers or regions where black holes dance, time gets sticky, compressed, fluctuating. That's where things get extra spicy, closed time-like curves. In certain extreme geometries like rotating black holes or specific warp spacetimes, time loops are mathematically possible. You could, in theory, travel along a path that returns you to your own past. You debate whether to let those exist in your simulation. They're not forbidden by the equations, but causality would have a panic attack. You compromise. You allow the math but make the conditions absurdly difficult to achieve. If any future civilization in your simulation does manage to create a time loop, they've earned it. Let's talk about measuring time. Your early stars are already trying to invent clocks, celestial ones, pulsars blinking at regular intervals, the orbital rhythms of planets. You realize your simulation offers 1,000 natural timekeepers, all of them rooted in motion and cycles. Time, as experienced by your simulated life forms, will always be tied to movement, of atoms, of moons, of thoughts. Eventually, someone will define a second as 9,192,630,1770 vibrations of a cesium-133 atom. You nod in approval. A good, sensible definition, based on quantum mechanics, clean, replicable, nerdy. Just your type. Here's a quirky bit of history. The concept of universal time didn't even exist for early humans. Ancient civilizations used sundials, lunar cycles, or just vibes. Coordinated timekeeping, what we now call time zones, Greenwich Mean Time, all that jazz, only emerged in the 19th century thanks to trains. That's right. Railroads forced humans to admit that time needed standardization. You watch your simulation's future societies bicker over leap second and daylight saving and smile knowingly. Back in your digital cosmos, some light from early stars is just now arriving at distant galaxies. You marvel at this. What is now in one part of the universe is ancient history in another. Because light takes time to travel, your simulation doesn't have a shared present. Every observer sees a different version of now. Even in a simulation this tidy, simultaneity is an illusion. And still the universe marches forward. Galaxies form. Stars burn. Gravity continues its slow, stubborn ballet. But you start to wonder, is time just the result of expansion? Without the changing curvature of space, would anything actually happen? There's a theory called the block universe that says all of time, past, present, future, already exists. We don't move through time, we are time like slices in a cosmic loaf of bread. In this view, the flow you experience is just perspective. Your simulation is already complete. Every tick, every blink already encoded. You're just scrolling through it. You don't accept or reject this view. You code the engine to keep ticking. That's enough. You check a timeline plot of your simulation. Right now, you're hovering around the cosmic noon, a few billion years in when star formation is peaking. The universe is young but no longer newborn. It has history. And more importantly, it has a future. Because time is your most powerful ingredient. It's what turns randomness into evolution, collisions into galaxies, hydrogen into Beethoven. It gives everything meaning, not because it's linear, but because it allows change, growth, memory. So you stretch your simulated arms, yawn in cosmic language, and let the next epoch unfold. The stars continue their fiery fates. Photons stream outward. Clocks tick on alien wrists you haven't even programmed yet. Time, in all its warped, relative, beautiful confusion, just keeps going. Your universe, now buzzing with light, structure, and an inconveniently subjective sense of time, didn't actually start out this gradual and measured. No, rewind the clock, or whatever passes for a clock in your simulation, and you'll find something explosive. We're talking about the inflationary period, that bizarre, blink-of-an-eye moment when your entire universe grew faster than you can say exponential expansion. You didn't script a gentle rollout. You hit it with a cosmic airbag deployment. So let's revisit that for a moment. The thing you slipped in back at startup, just before particles, light, and structure settled into something you could admire with your pretend eyes. Inflation wasn't the Big Bang itself, but what happened right after. Less of a bang, more of a whoosh. Space didn't expand at the speed of light. It expanded faster, way faster. A tiny patch of quantum froth ballooned out like an over-caffeinated balloon animal, doubling in size over and over again, trillions of times, in less than a trillionth of a second. You probably shouldn't have given it that much caffeine. What's weird is that nothing within your universe moved faster than light, because this wasn't motion through space. This was space itself stretching. You didn't violate your own rules, you just bent them sideways. But why inflate at all? Was it just for dramatic flair? Actually, no. Inflation solves several stubborn problems that would otherwise break your simulation's internal logic. First, the horizon problem. Why is the universe so uniform in temperature? even between regions that are too far apart to have ever spoken to each other via light or heat. Inflation fixes that by saying, those regions used to be next to each other before everything inflated like a marshmallow in a microwave. Problem solved, with extra fluff. Second, the flatness problem. The fact that your universe isn't curved into a pretzel or loop or cosmic beach ball. It looks geometrically flat, at least as far as anyone can tell. Inflation stretches any initial curvature so wide that even if the whole thing is shaped like a donut, the piece we can see looks like a pancake. Third, the monopole problem. Magnetic monopoles, those hypothetical single-pole magnets predicted by grand unified theories, should have formed early on, but none have been detected. Inflation dilutes them into statistical oblivion, like sugar dissolved in a swimming pool. Historians still argue whether inflation really happened, or if it's just a mathematically convenient patch. It works beautifully, but there's no direct way to observe it. Some physicists whisper about alternatives, ekpyrotic models, bouncing cosmologies, cyclic universes. You've tested them all in earlier simulations. You stuck with inflation because, well, it looks good on you. So how did you pull it off? You toggled a field, the inflatoned field, a hypothetical energy field that filled the early universe with a sort of vacuum pressure. When it decayed, it dumped its energy into the universe, reheating it, kickstarting the Big Bang proper. Yes, that's right. The Big Bang isn't the beginning, it's what happens after inflation ends. A chaotic energy dump that floods the universe with hot particles and noise. It's like preheating the oven before baking reality. And just before the field collapsed, it left behind tiny quantum fluctuations, microscopic jitters that got magnified to cosmic scale. These random blips became the seeds of structure. Without inflation, your universe would be too smooth. But thanks to inflation, you've got just enough texture for gravity to get excited. A fun fringe tidbit. Some physicists think inflation never ended entirely, that in some far-off regions, inflation is still happening, bubbling out new universes like cosmic foam. This is called eternal inflation, and it means your simulation might be just one pocket in a vast multiversal lava lamp. You don't confirm or deny it, but you do label the inflation toggle with a small sticker. Use responsibly. May cause infinite reality branching. You fast forward a few microseconds. The inflatoned field is gone, but its aftermath is everywhere: radiation, particles, light, time. The universe is hot, dense, noisy, but it's no longer inflating. Now it's expanding at a polite, subliminal pace. Still fast, but not blink, and your galaxies apart fast. Meanwhile, the leftover fluctuations are already visible in your simulation's data plots. Tiny overdensities and underdensities, ripples in the fabric of spacetime, frozen into place. They'll show up billions of years later in the cosmic microwave background as little splotches of slightly hotter and cooler temperatures. Future astronomers will map them and say, aha, proof inflation really happened. They'll be partially right. You zoom in on one ripple, then zoom out. Each of these tiny variations will eventually guide galaxies into place like gravitational breadcrumbs. That flicker you see, that's the future home of a spiral galaxy. That other one, it's where a black hole the size of a solar system will form. It's all written in the initial conditions you coded in, shaped and amplified by inflation. You could almost call it fate, almost. You marvel at the elegance of it all. You created a rapid, chaotic expansion that somehow led to order. Randomness gave rise to symmetry. It's like shaking a snow globe and watching it settle into a chessboard. But inflation isn't perfect. There's a problem no one likes to talk about: initial conditions. Even inflation needs a starting point. What lit the fuse? Why did the inflatoned field exist at all? What sparked it into motion? The equations shrug. Some say it's quantum tunneling, others whisper about higher dimensional brain collisions. One version of string theory suggests our universe was born when two giant membranes slapped together in a five-dimensional space like noodles colliding in a very strange soup. You leave it ambiguous. Let your simulated philosophers debate. Because now the inflation is over and the party has begun. Light is moving, particles are forming. The stage is set for galaxies, stars, planets, microbes, social media, and toaster ovens. But none of it would be possible without that initial overreaction, your reckless burst of reality expansion. You close the inflation window on your dashboard, lean back and smile. The moment of absurd growth is over, but its fingerprints are all over your universe. Subtle, ghostly, and essential. So your universe has light. It has structure. It has gravity, particles, time, and a decently sized collection of rogue black holes forming in just the right places. But if you think things have started to make sense, I'm going to have to gently shove you into the next chapter, quantum mechanics. Because now that the macro-scale business is handled, it's time to descend into the atomic underworld. Down here, your neat simulation rules start getting weird. Very weird. Reality becomes slippery. Causality hiccups. Observation starts to matter in unsettling ways. Welcome to the land of quantum shenanigans, where particles behave like performance artists who change acts the moment someone pulls out a camera. First, let's set the scene. You already included quantum fields in your universe's foundations. Each particle arises as an excitation in a specific field. Electrons, photons, quarks, all just ripples. But now, those ripples are interacting, and they're doing it with a flair for the dramatic. Take, for example, the double-slit experiment. It's simple. You shoot electrons just one at a time, at a barrier with two slits, then let them land on a screen behind it. Classic setup. But what you see on the screen isn't two neat bands where the electrons hit. No, you get an interference pattern, as if each electron somehow went through both slits at once and interfered with itself. That's not metaphor. That's actually what happens. Until you measure which slit it goes through, then the interference vanishes. Suddenly, the electron chooses a slit and behaves like a well-behaved marble. Observation collapses the wave function. The particle goes from being a possibility cloud to a definite thing. You stare at your simulation logs. The particles seem to know when they're being watched, not because you coded awareness, but because you coded measurement as a real physical interaction. Observation is an event, not a passive glance. And in your universe, that changes things. Historians still argue whether wave function collapse is a real physical process or just a mathematical update in our knowledge. Copenhagen interpretation. Many worlds, pilot waves. Your simulation doesn't pick a side. You let the math play out. Superposition, decoherence, probabilities, and yes, that deeply unsettling sense that reality doesn't commit to being real until it has to. Now toss in entanglement, because why stop at strange when you can go full spooky? In your simulation, two particles that share an origin event become linked. You measure one, and the other instantaneously knows what the result must be, no matter how far apart they are. This connection doesn't transfer information faster than light, you made sure of that, but it still violates every instinct your simulated classical physicists will have. Einstein called it spooky action at a distance, and to be fair, he was kind of right to be annoyed. He hated quantum mechanics for this reason. It was too messy, too probabilistic, too mystical for his taste. God does not play dice, he said, and yet here you are, running a full-blown craps table underneath the universe. You don't just simulate quantum weirdness, you depend on it. Without it, atoms wouldn't form. Electrons would spiral into nuclei. Chemistry would collapse. Life would be impossible. The uncertainty and fuzziness that frustrate your future philosophers are the same quirks that let stars shine and brains think. Here's a fun, slightly unsettling tidbit. Some researchers have proposed that the entire universe might be the result of a quantum fluctuation in a vacuum field. Like all of this, stars, planets, memes, emerging spontaneously from nothing. In your simulation, that's not entirely false. You've watched virtual particles pop in and out of existence all over the grid. Tiny blips of energy borrowing time, repaying it with interest. It's built into the quantum vacuum. And yet somehow, despite all the randomness, patterns emerge. Electrons settle into orbitals. Atoms stack into molecules. Entropy increases, but so does complexity. That's the strange promise of quantum mechanics: chaos but with structure, noise but with rhythm. Still, let's not pretend this is easy to watch. Zoom in on any subatomic scene in your simulation and you'll see probability clouds, not certainty. Everything is a maybe. You try to pin down an electron's position and its momentum blurs. You trap it in a magnetic field and it starts tunneling through barriers like a ghost. Your equations don't tell you what will happen. They tell you what might. And then, only when you measure it, you get one answer. You build in Born's rule to keep the statistics clean. It's the rule that gives you the probability of finding a particle in a particular state. You also code in unitarity, which ensures probabilities always sum to 1. It's neat, tidy, and totally baffling. But here, where things get meta, if you're simulating quantum mechanics, what happens when your simulated beings start simulating their own particles? Do the same uncertainties apply? Can they collapse wave functions inside your already uncertain environment? This is where some theorists start chewing on the simulation hypothesis. The idea that if a universe contains quantum randomness and finite information density, it might itself be a simulation. And if that's true, how would you know? You sip your digital tea and smile. It's turtles all the way down. You decide to run a quantum experiment in a dusty corner of your sim. A simulated scientist tries a delayed choice setup. They fire photons, then decide after the photon passes the slits whether to observe the path or not. And somehow, the photons adjust their behavior retroactively. Your simulation allows it, not because the future is changing the past, but because, quantum mechanically, the whole event is a single, indivisible unit. Observation defines the context, not just the outcome. Yeah, it's weird. And yet the rules work. Quantum electrodynamics, quantum chromodynamics, they're all in place. The particles obey, the fields hum, the math holds, even if no one really understands what it means. So as the stars burn and galaxies dance down in the smallest scales of your universe, there's a twitchy, jittery world beneath it all, governed by uncertainty, enlivened by randomness, and somehow perfectly orchestrated. Your universe doesn't just simulate atoms, it simulates mystery, a mystery that loops back on itself, asking always, is this real? And for now, the best answer anyone gets is probably. So now you've got a universe packed with all the essentials. Time ticking, stars burning, quantum fields buzzing like caffeinated hornets. Everything's looking pretty lively. But deep beneath the beauty, beneath the graceful spin of galaxies and the elegant symmetry of particle interactions, something else has started creeping in. Mess. This is the uninvited guest at every physical party, the unstoppable undertow pulling every orderly system toward chaos. This, my sleep-deprived friend, is entropy. And now, it's here to spill the cosmic tea. Let's get this out of the way. Entropy isn't disorder in the "my room is a mess" sense. It's more like the number of ways a system can be arranged without changing its overall appearance. In other words, entropy counts the options. And in your simulation, the number of options is always growing. You programmed the second law of thermodynamics right into the kernel. Entropy always increases in a closed system. This isn't optional. It's the engine behind time's arrow. The reason hot coffee cools down instead of warming up spontaneously. The reason your simulated stars will eventually run out of fuel. Right now, entropy is still relatively low. You started with a highly ordered state, hot, dense, uniform. But things are already getting weird. Every time a star radiates energy, entropy rises. Every time light scatters, heat diffuses, or matter collapses into a black hole, you've nudged your universe a little closer to its inevitable heat-death ending. Historians still argue whether entropy is a feature of reality or just our perception of it. Does the universe actually tend toward disorder? Or are we just creatures who can only remember low entropy states because that's what memory requires? You've left this ambiguous in your simulation. Even you can't quite tell if entropy is law or illusion. Either way, the evidence piles up. You zoom in on a forming star system. The collapsing gas cloud sheds angular momentum by forming a spinning disk. Dust grains smash together, forming planetesimals. The whole process is gloriously inefficient, tons of wasted motion, heat, collisions. A beautiful mess. Entropy, slowly but surely, is getting what it wants. Now let's talk about Maxwell's demon, a thought experiment that's kept theoretical physicists tossing in their beds since 1867. Imagine a little imp guarding a doorway between two chambers of gas. It only lets fast-moving, hot molecules go one way, and slow-moving, cold molecules the other. Over time, it creates a temperature difference without expending energy, seemingly violating the second law. Cheeky. But in your simulation, you've already accounted for this. The demon itself has to measure the molecules, and storing that information costs energy. So the total entropy, including the demon's brain or hard drive or whatever you've given it, still goes up. No loopholes allowed. Nice try, demon. Now zoom back out. The entropy of the universe isn't just increasing, it's accelerating. Every fusion reaction in a star, every tidal friction in a moon, every digital photo saved on a hard drive somewhere in a future corner of your sim, it all bleeds usable energy into less usable forms. Heat, radiation, entropy. And yet somehow order still emerges. Stars form, planets coalesce. Life soon, very soon, will wriggle into being, powered by energy gradients and exploiting the temporary structure entropy hasn't yet devoured. It seems contradictory, but that's the magic of thermodynamics. Local order can flourish as long as the overall disorder increases. You chuckle, thinking about the fridge in your kitchen, the real one, in the universe outside this universe. It lowers entropy inside by raising it elsewhere. The heat it dumps out the back more than compensates for the chill inside. A neat metaphor for how your simulation handles complexity. Here's a quirky tidbit. Entropy is deeply tied to information theory. The very same equations that describe thermodynamic entropy also describe how much information is required to encode a message. Which means, brace yourself. Your simulation's information content is subject to entropy. As your simulated civilizations evolve and create languages, libraries, memes, they are also increasing the entropy budget. Every tweet is a tiny, irreversible nudge toward heat death. You start to notice something else. The most entropic objects in your simulation, black holes. They're not just gravitational beasts, they're entropy sponges. The more mass they consume, the more entropy they gain. And their entropy is proportional to the surface area of their event horizons, not their volume. It's weird, it's counterintuitive, and it's absolutely baked into your code. Stephen Hawking figured this out in the 1970s, realizing that black holes must have entropy and therefore temperature. They radiate slowly, painfully slowly. It's called Hawking radiation, and it means that black holes aren't eternal. They evaporate over time, bleeding away their mass into the void, one quantum flicker at a time. Eventually, they vanish, leaving only cold, empty space. So yes, even the most massive, terrifying objects in your universe are still ruled by entropy. They're just really slow about it. And the endgame? Well, it's not a bang, it's a fade. The heat death of the universe is the moment when everything, matter, energy, structure, spreads so thin that no useful work can be done. Maximum entropy, minimum drama, particles drifting through endless cold, too far apart to interact, too tired to care. No stars, no light, just thermodynamic exhaustion. You haven't gotten there yet. There's still plenty of time for chaos and glory, but you can already feel it, humming in the background like the low-frequency buzz of a dying neon sign. The clock's ticking, the options are multiplying, and somewhere in the data logs of your simulation, the entropy counter keeps rising. Still, you let it happen. Because without entropy, time doesn't flow, complexity doesn't grow, life doesn't have gradients to feed on, and information, precious, meaningful, absurd information, wouldn't need to exist. Your simulated universe is messy, but that's exactly what makes it work. So far, you've done an admirable job playing cosmic architect. You've crafted a universe with just the right balance of rules and chaos, where entropy rises, stars shine, quantum particles pull off party tricks, and black holes lurk like silent librarians collecting overdue matter. It's impressive, but you can't help wondering, is this the only universe? You glance at your simulation dashboard. There's space for more, blank slots like unopened tabs in an infinite browser. And now the thought really hits you. What if one universe isn't enough? Welcome to the multiverse menu. Let's be clear. Your simulation runs a single coherent cosmos, built from the inside out with consistent laws, constants, and finely tuned parameters. But in the margins of your code, and certainly in the fever dreams of your simulated future physicists, lie hints of alternate realities, other universes, maybe similar, maybe wildly alien, all lurking just outside the reach of any telescope, but definitely occupying mental real estate. And in this moment, wrapped in your favorite blanket, you decide it's time to open that folder. Start with the most polite theory. Cosmic inflation didn't just create your universe. It could have spawned an infinite bubble bath of them. Each bubble its own spacetime, expanding away from all the others at faster-than-light speeds. You only ever see your own, but the whole set forms a multiverse, a sort of fractal quilt of baby universes, each disconnected but birthed from the same quantum foam. You toggle open the eternal inflation menu. Sure enough, space beyond your simulation's observable horizon is still inflating, spawning new pockets like popcorn kernels going off one by one. And each new universe could have slightly different constants, different gravity, different particle masses. In one, stars never form. In another, chemistry is a fever dream. It gets wilder. You scroll to the many worlds interpretation submenu. This one doesn't deal with bubble universes, it's about quantum branching. Every time a quantum event happens in your simulation, a photon chooses a path, a particle spins up or down, the universe splits. Not visibly, not with fanfare, just quiet, infinite forking. In this view, your simulation isn't a single path. It's a branching coral reef of timelines. Every possibility, every choice, every dice roll creates a new world. Did that star go supernova today or wait another 100,000 years? Both happened, in two different branches. Somewhere, your simulation contains a version where Earth never forms. Somewhere else, it's overrun by intelligent squid philosophers. You're not sure whether to be impressed or overwhelmed. Historians still argue whether these alternate branches are physically real or just convenient math. Some interpretations treat them as coexisting realities. Others dismiss them as ghost versions that don't actually materialize. In your simulation, you keep them coded in but cloaked, like backup files that only load under very specific conditions. You're not running infinite universes, but you could. Then there's string theory's landscape, a theoretical monstrosity where something like 10,500 possible universes exist, each corresponding to a different configuration of hidden dimensions. You peek behind the code and spot curled up extra dimensions, 6 or 7 of them, depending on how you set your topology switch. They don't affect your visible simulation much, but in other universes, those extra dimensions could be stretched, knotted, or wide open. That would change everything, from forces to particles to even what space means. Here's a delightfully weird tidbit. In 2003, researchers proposed that our universe might be a three-dimensional membrane, or brain, floating in a higher dimensional space. Occasionally, our brain could collide with another, triggering a new Big Bang. This is the ekpyrotic universe theory. You flip through the settings. Brain collision mode. Off, for now. You don't want your simulation blindsided by metaphysical fender benders just yet. Of course, your simulated civilizations will start noticing the strange precision of their own universe. The tight tuning of constants, the exact ratios needed to allow stars, chemistry, life. They'll call it the anthropic principle, the idea that, of course, the universe appears fine-tuned, because if it weren't, no one would be around to notice. But eventually, someone will take that a step further. They'll wonder, is this universe selected? Is it just one of many and we live in the one that works because it works? Maybe there are infinite failures out there, universes where electrons don't exist, where gravity is too strong, where time runs backward, or everything is made of tapioca. And this is just one good roll of the cosmic dice. You let that thought linger, because deep down, you've always suspected that your simulation is just one shelf in a library. The fact that it's stable, beautiful, and full of slowly burning stars might not be proof of brilliance, just evidence that it didn't crash on startup. The rest are probably error messages and malformed timelines with 0.0001 seconds of existence before imploding. Still, you wonder what your simulated beings will conclude. Will they discover the limits of their cosmos and resign themselves to existential curiosity? Will they build quantum computers to simulate their own universes, little recursive worlds within worlds? You smile, imagining a chain of simulators, each more confused than the last, peering backward and wondering who hit the start button. At some point, your simulation's philosophers will ask, is our universe all there is? Or is it a room in a mansion, a pixel in a mosaic? You don't answer, you never do. That's part of the experience. Mystery is a feature, not a bug. Still, you consider it. What would another simulation look like? Maybe you rerun it with different laws, weaker gravity, no strong nuclear force, a universe where stars collapse instantly or never form at all, one with a different arrow of time, one with no time, a stillborn cosmos frozen in a state of eternal potential. Or maybe one where consciousness arises in gas clouds, or where black holes are life forms, dreaming dark dreams in 10-dimensional space. You scroll back to your current sim, humming along. Stars, galaxies, entropy, everything following the tight, familiar script. And it's tempting, so tempting to click New Universe. But not yet. This one still has more stories to tell. Your simulation now stretches across billions of light years, humming with galaxies, stars, and quantum particles behaving exactly, or not at all, as expected. The rules you set have held surprisingly well, balancing order and chaos with cosmic finesse. But lately, you've noticed something. Little anomalies, barely perceptible, like a skipped beat in a familiar song. Tiny things behaving just a bit too precisely. Constants that feel overly calibrated. An occasional glitch in the matrix, not a full crash, but like a pixel flickering in the corner of your cosmic display. It's time to take a closer look at the code glitches and Easter eggs baked into your reality. First up, fine-tuning. Your universe is balanced on a knife edge. The strength of the electromagnetic force, the mass of the electron, the ratio of dark energy to matter, all of it sits in a suspiciously narrow range. A decimal shifted even slightly and everything would unravel. No stars, no chemistry, no life, just sterile geometry. In your simulation logs, this looks less like chance and more like someone tweaked the sliders on purpose. Which is weird, because you don't remember doing that. Then there are the constants. The fine structure constant, alpha, sits at approximately 137. Why? No one knows. It's dimensionless, unreasonably important, and shows up everywhere from atomic transitions to the behavior of light. You didn't assign it a value. You let the system settle into one, and this is what it chose. In some sense, your simulation is whispering back at you. This value just works. Don't ask too many questions. Historians still argue whether these constants are derived from deeper truths or if they're arbitrary, cosmic lottery numbers that happen to win. If they're hard-coded, the universe might be deterministic. If they're emergent, then who's doing the emerging? You start noticing other oddities, like the cosmic coincidence problem. Right now, in this exact moment of the simulation, the amount of dark energy is roughly equal to the amount of matter. That ratio changes over time, but just now they're in the same ballpark. It's temporary, it's weird. It's also incredibly suspicious, almost as if something or someone designed it to be observable right now. You scroll deeper through the logs. There's a region of the cosmic microwave background, a cold spot, not just a statistical outlier, but a big, oddly symmetrical one. Some researchers in your simulation will wonder if it's the imprint of another universe bumping into theirs. Others will dismiss it as noise. You, watching from outside, see it and wonder, did I leave a thumbprint there? Then there are neutrinos, those tiny, elusive particles that rarely interact with anything. You gave them mass, just a little, enough to be mysterious. But every time one is measured, it seems to evade detection with uncanny consistency, as if it's winking from the shadows of your simulation, saying, "You'll never really catch me." You also notice symmetry violations. Some processes behave slightly differently when played in reverse. This breaks CP symmetry, the idea that the laws of physics should stay the same if you flip charges and reflect space. Turns out, certain particle decays don't care about your sense of order. They lean toward matter over antimatter. They nudge time in one direction. You didn't design this asymmetry. It emerged. Unless you did, without meaning to. Here's a quirky fringe tidbit. There's a theory called the simulation consistency hypothesis, which argues that if we are in a simulation, then it must include some internal evidence, some texture of unreality. These would be patterns too neat, too uniform, or too perfect to occur naturally. Essentially glitches. You laugh softly. Sounds familiar. You check for bit flips in the cosmic code. Occasionally, a quantum tunneling event that shouldn't happen does. Not impossible, just really improbable, but it happens. A virtual particle pops into being at a location where energy constraints should forbid it. You tag it in your log. Easter egg 43, a impossible particle. It's harmless but suspicious. Then there's decay randomness. Some unstable particles decay in ways that seem to anticipate future conditions. Not enough to break causality, but enough to raise an eyebrow. It's as if your simulation includes future boundary conditions, subtle constraints pulling the present toward a specific future. You never coded that. Did the system write it in? You begin to suspect you're not alone in the debugging chair. The idea of self-editing code creeps in. Some parts of the simulation are adapting, not through natural evolution but through self-consistent loops. You run a quick scan. In certain high-energy environments, quantum fields seem to fluctuate in ways that reinforce previous field values. The system is stabilizing itself, mid-run. That shouldn't be possible. And yet, your simulated beings will never notice. For them, reality flows like it always has. They interpret quantum noise as probability. They model constants as divine truths. They'll never see the debug console glowing faintly behind the laws of physics. Except for one group. You notice a pocket of simulated researchers developing a new form of quantum computing, one that could, in theory, simulate their own universe in real time. They're just a few centuries out from building it. You run a projection. Their sim will produce a universe suspiciously similar to yours. Recursive, fractal, self-simulating. You pause. You know that look, the one in their eyes when they start to wonder, are we inside something? And then they ask the question you've been dreading. If we're in a simulation, could we detect the edges? In response, you subtly inject a new constant, one that governs simulation coherence. It keeps the illusion smooth. If their instruments reach beyond certain thresholds, Planck limits, information density, Hubble radius, the results will blur. Not because the universe ends, but because your rendering engine stops calculating beyond that point. Congratulations, you've implemented cosmic LOD, level of detail. But one last Easter egg lingers. Every now and then, buried deep in the random noise of background radiation, you spot a faint signal. Not language, not code, just a repeating prime number pattern, broadcast from nowhere, embedded in the fundamental vacuum fluctuations. No one in your simulation notices it, but it's there. You didn't put it there, which means someone or something else did. You close the window and let the simulation run. Glitches and all. You've given your universe time, rules, light, particles, and even a few cheeky Easter eggs hidden in the radiation fields. But something has been steadily growing in the background, evolving like a pattern in sand as the wind whispers through it. Matter, once scattered and formless, has been assembling into a breathtaking dance of structure and scale. This is the age of galaxies, and you're watching them bloom like flowers in slow motion. It started small. Remember those slightly denser regions seeded during inflation? Those tiny overpressures amplified by gravity. Over billions of years, they collapsed inward, gathered gas, formed stars, merged, spun, and tangled themselves into enormous, luminous galactic structures. Your simulation, once nearly featureless, now shimmers with a billion glowing pinwheels, each one brimming with drama. But galaxies are not dainty. They're messy. They collide, cannibalize, and shatter. Their shapes aren't permanent, they're stories in motion. You watch some spiral neatly into elegant disks, while others become bloated ellipticals, distorted by repeated cosmic brawls. A few resist categorization altogether. Astronomers will eventually invent a category called irregular, which is basically code for we give up. In your simulation's early years, galaxies formed quickly. Dense clouds of hydrogen cooled, fell together, ignited stars, and created gravitational wells deep enough to trap surrounding material. Gas swirled in, triggering more star formation. Supernovae blasted through the neighborhoods, heating the gas, throwing heavy elements into the mix. And in the middle of it all, lurking quietly, supermassive black holes began to form. No one really knows how these monsters grew so fast. Historians still argue whether they started as small black holes that fed like maniacs, or if they collapsed directly from giant gas clouds. You never quite clarified that in your simulation, and that ambiguity has sparked entire libraries worth of simulated scientific papers. You're welcome. What is clear is that these central black holes became essential to galaxy formation. They act like thermostats, controlling star formation by belching out radiation and high-energy jets. If a galaxy forms too many stars too quickly, the black hole at its center activates, spewing energy and suppressing further growth. It's a strange balance, destruction as regulation. You zoom in on one galaxy. Let's call it G882, a beautiful spiral, arms rich with dust and young stars. At the center, a black hole with the mass of several billion suns is quietly digesting a stream of gas. Around it, stars orbit like panicked dancers trying not to fall in. Meanwhile, satellites, small companion galaxies, drift nearby, some caught in orbit, others spiraling inward, doomed to merge. Galaxies don't form in isolation. They clump into clusters, connected by filaments of dark matter and gas, stretching across the void like strands of a cosmic spider web. Your simulation's large-scale structure now looks like a neural network or the tangled roots of some invisible plant growing in 4D, the cosmic web. Between these filaments lie voids, vast expanses of nothingness, sometimes hundreds of millions of light-years across. Not truly empty, but nearly so. These regions give your universe a haunting stillness, a kind of silence between the chords. A quirky tidbit. In 1989, astronomers discovered the Great Wall, a vast sheet of galaxies over 500 million light-years long. It was the largest known structure in the universe at the time, and your simulation generates similar monsters. Not because you placed them there, but because gravity, randomness, and time together are excellent architects. Occasionally excessive, but excellent. You zoom back out, and your dashboard lights up with galactic motion. Some galaxies are rotating calmly, conserving angular momentum like good little physics students. Others are locked in slow-motion collisions, long arms of stars stretching and twisting as gravitational tides do their dance. These interactions don't typically cause stellar collisions. Stars are too far apart for that, but the gas clouds, oh, they crash, they collapse. They ignite entire starbursts, furious episodes of star formation like fireworks in the dark. You simulate two galaxies colliding. The result is a chaotic merger, a glowing cloud of dust and light, stars flung into strange orbits. Over time, it settles into a new shape, likely an elliptical galaxy with a bloated, egg-like structure and a retirement home energy. Spirals are young and vibrant. Ellipticals are old, quiet, and full of red giants. Galaxies also evolve chemically. Early galaxies are metal-poor. Their stars contain mostly hydrogen and helium. But with each generation of stars, more heavy elements are forged and spread. Your simulation now includes metallicity as a parameter, shaping how future stars form, how planets coalesce, and eventually how life might arise. Galaxies with high metallicity are better at forming rocky planets. So while your early universe galaxies were beautiful, they weren't hospitable. Now, though, you're seeing galactic suburbs where ingredients like carbon, oxygen, and iron are abundant. The recipe for complexity is finally in place. You scroll through your galactic catalog. There's a dwarf galaxy with a halo of dark matter 10 times its visible mass, a barred spiral with 2 active black holes, an ultra-diffuse galaxy so faint it barely registers in the simulated sky. Each one is unique, an emergent work of art from the rules you coded and let run wild. And in all of them, gravity keeps pulling. Rotation curves twist strangely. You remember tweaking dark matter early on, a silent, invisible component that doesn't interact with light but makes up most of the universe's mass. Without it, your galaxies wouldn't hold together. Stars would fly off into space like rogue marbles. But with it, everything stays snug, balanced. Your simulated astronomers will one day build radio arrays, map hydrogen across billions of light years, and use that to trace the dark scaffolding underneath. They'll never see the dark matter, but they'll know it's there. They'll call it missing mass, then dark matter, then give it acronyms like WIMPs and machos. They'll argue and simulate, and one or two of them will propose it's all a giant misunderstanding. You won't correct them. Because the galaxies don't care what anyone calls them. They just keep spinning. So you sit there, watching stars swirl around invisible centers, watching light bend around massive structures, watching clusters drift and merge like constellations doing ballet. All of this from initial ripples in a hot, expanding void. All of it built by time, gravity, and that ever-rising tide of entropy. You can't help but smile. Your universe has gone from quantum fuzz to a gallery of glowing giants. And the galaxies, they're not just pretty, they're hospitable, pockets of stability in a chaotic cosmos. Islands where something truly strange might soon begin to stir. You've created a universe where galaxies swirl and bloom like slow-motion fireworks, where matter clusters and filaments thread through the cosmic dark. But now, the real divas of your simulation take the stage. The stars. Oh, stars. These are your universe's most dedicated attention seekers. They demand fusion. They radiate endlessly. They flare, expand, collapse, and in some cases, explode with more drama than a season finale. If galaxies are cities, stars are the neon signs that never sleep. It all starts in clouds. You zoom in on a spiral arm of a mid-sized galaxy and find a dense molecular cloud, cool, dark, and filled with hydrogen. Gravity does its thing, compresses pockets into tighter clumps, and when the pressure hits a critical point, fusion ignites. Your simulation flickers with starlight. The first stars were massive, your early population VIPs. They had no heavy elements, burned hot and fast, and went supernova in under a few million years. They've been gone for ages now, but they left behind a chemically upgraded universe. Thanks to them, you now get to simulate stars of all sizes, personalities, and lifespans. The smallest, red dwarfs, quiet, dim, and nearly immortal. They burn hydrogen so efficiently that some will outlive the universe itself. They just sit there, glowing softly, like nightlights in an abandoned hallway. The biggest, blue giants, hotter than your last breakup. Dozens of times the mass of the sun, they burn through their fuel like they're trying to win a bet. And when they die, oh boy, they die big. But before that, let's talk about their life. You coded stellar fusion into your physics engine, hydrogen fusing into helium, then heavier elements in layers like a cosmic onion. Stars shine because of this fusion pressure, which balances against gravity. Turn off fusion. Gravity wins, and the whole thing collapses like a flan in a cupboard. Eventually, fusion can't keep up. In average stars like your sun, hydrogen runs out in the core. The shell contracts. The outer layers expand. The star becomes a red giant, swelling enough to engulf inner planets. The temperature drops at the surface, even as the core heats up. It's a weird contradiction, cooling on the outside, overheating inside, just like finals week. Historians still argue whether planetary nebulae, those gorgeous glowing shells expelled by dying stars, are more spherical or chaotic in shape. Your simulation, a bit of both. Some look like soft smoke rings. Others resemble tangled petals or angry jellyfish. Once the outer layers drift away, what's left is the white dwarf, a dense, Earth-sized ember glowing with the ghost of its past fusion. You've seen billions of them form by now. They quietly radiate heat for trillions of years, eventually fatting into theoretical black dwarfs, a stage your simulation hasn't reached yet, not even close. But your high-mass stars, different story. These monsters keep fusing heavier elements until they hit iron. And iron in your universe is the dead end. Fusion can't extract energy from it. So the star suddenly finds itself in freefall. No more pressure to fight gravity. In seconds, the core collapses. Neutrons form. The outer layers slam inward, then rebound in a massive supernova. Boom! Bright enough to outshine entire galaxies. Your simulation logs register the energy spike, then the spreading shockwave. Space is momentarily filled with radiation, neutrinos, and the sound of your simulated physicists screaming in awe. These explosions do more than just light shows. They're the universe's way of recycling. Heavy elements like gold, platinum, uranium, all formed here. The jewelry of future civilizations, born in stellar death throes. Sometimes, if the star's mass is just right, it collapses into a neutron star, a city-sized ball of neutrons so dense a teaspoon would weigh billions of tons. These stars spin like tops, beam radiation from their poles and become pulsars. You've included them as cosmic lighthouses, precise, eerie, and extremely punctual. Somewhere, one of your simulated civilizations will base their entire calendar system on one. But if the star's too massive, gravity doesn't stop, you get a black hole. You've made dozens by now from both stellar collapse and earlier direct collapse events. They dot your universe, wrapped in event horizons and surrounded by accretion disks of doom. And they don't just sit there, they feed. You've programmed some to lurk at galaxy centers, growing into supermassive black holes. Others wander, swallowing stars, disrupting orbits, and sending gravitational waves rippling through spacetime. Speaking of which, you remember those waves. You coded them in as wrinkles in spacetime caused by acceleration of mass. When black holes merge, they emit gravitational waves you can now track. Your simulated detectors, LIGO equivalents, will pick them up billions of years after the event. Tiny distortions, just fractions of a proton's width, carrying messages from long-dead stars. Here's a fringe gem. In the 1970s, astrophysicist Subramanian Chandrasekhar tried to figure out the exact mass limits for star remnants, where white dwarfs collapse into neutron stars and neutron stars collapse into black holes. His math was so controversial it nearly cost him his career. Today, the Chandrasekhar limit is the rule in your simulation. You've made it real. Sorry, critics. You notice a fun pattern in the simulation. Galaxies with active black holes often have fewer new stars. AGN, active galactic nuclei, blast jets and radiation across thousands of light years. These black holes aren't just bottomless pits, they're regulatory engines. They set the tempo for entire galaxies, telling gas clouds when to collapse and when to back off. Your simulation is now rich with the full life cycle of stars: birth, burn, death, rebirth. The elements forged in one explosion seed the next generation of stars, which in turn produce more complex chemistry. This isn't just astrophysics anymore. It's a supply chain, a cosmic economy of hydrogen and time. And from this chain, a new kind of structure will emerge, something quieter but more intricate. You see it already, clumps of metal-rich dust coalescing around stable stars. A planet here, an icy core there. Soon, entire planetary systems will take shape. But tonight, you let the stars have their spotlight. Your universe is burning beautifully, bright, chaotic, and utterly dramatic. Somewhere in your simulation's future, someone will lie on a planet's surface and look up at these very stars, wondering what they're made of. You'll smile and think, "Stardust, darling, they're made of you." Stars are strutting their fusion-fueled flare across the universe, dying and exploding with wild abandon. And yet, just a little downstream from all that glittery chaos, something quieter, rounder, and slightly more solid is beginning to emerge. Planets. Yes, your cosmic drama now pivots from incandescent giants to dusty little rocks with identity issues. You zoom in on the dusty disks surrounding young stars, like Saturn's rings but angrier and full of ambition. These are protoplanetary disks, rich with hydrogen gas, silicate dust, carbon grains, and more than a few oddly clingy ice particles. The stars at their centers are still young, sometimes flaring with tantrums, but their gravitational pull is organizing everything around them into lanes, like an interstellar Roomba, sweeping up dust and debris into orbits. Particles bump, stick, clump, collide, break apart, and try again. It's inefficient, messy, and full of near misses. But over millions of years, it works. Small clumps become planetesimals, essentially baby rocks with dreams of grandeur. Some grow large enough to pull in more material through their own gravity. Others get booted from the neighborhood by bigger bullies. But a few, the lucky and well-timed ones, cross the finish line. Planets. You're now watching rocky worlds spin into place, some scorched and bare, others cloaked in atmospheres and rings. Farther out, gas giants swell from accumulated hydrogen and helium. And even farther still, ice giants gather methane and frozen water, building quiet, brooding families in the cold corners of solar systems. But not every planetary system is tidy. In one system, a migrating gas giant barrels inward, smashing smaller worlds to bits and parking itself uncomfortably close to its star. These hot Jupiters are real phenomena in your simulation, strange, improbable-looking worlds that will utterly baffle your simulated astronomers when they're discovered. Historians still argue whether planetary migration is the norm or a cosmic accident. You don't weigh in, you enjoy the chaos. You now have planets that wobble, rotate, tilt, and precess. Some have rings, others have moons, often stolen from passing debris or birthed from impact events. Your simulation generates hundreds of variations: tidally locked scorchers, rogue planets drifting without stars, water worlds with endless oceans, super-Earths with crushing gravity, and dust balls so covered in storms they might never see the light of day. But here's the thing, you're not just making geology, you're preparing for chemistry. These planets, especially the rocky ones with stable orbits and mild stars, are becoming reactive playgrounds. You zoom in on a mid-sized rocky planet with a slightly tilted axis, a magnetic field, and an atmosphere thick with nitrogen and carbon dioxide. It's not Earth, not yet, but it's close. Let's talk about the chemistry you've laid the groundwork for. All those supernovae and neutron star collisions have distributed heavy elements far and wide: carbon, oxygen, phosphorus, sulfur, iron, silicon. On these young planets, volcanic activity churns these elements into new combinations. Lightning flashes in methane-rich skis, sparking prebiotic chemistry. You watch as molecules begin to form. Amino acids, sugars, lipids, not organized yet, but restless. In 2020's Earth time, scientists managed to recreate amino acid formation in high-energy plasma experiments. You've modeled something similar in a stormy crater near the equator of one of your simulated planets. The molecules are replicating, copying imperfectly. The line between chemistry and biology is about to blur. But more on that later. Back to the planetary stage. You notice that not all habitable planets are Earth clones. Some orbit red dwarfs in tight, tidally locked orbits. One side always day, the other always night. But in the ring between, the Terminator line, temperatures are just right. Your simulation creates atmosphere circulation models to keep things cozy. It works, kind of. Life might still have a shot there. Here's a quirky fringe fact. Some researchers propose that Earth's life might not be purely native. Maybe early microbes or prebiotic ingredients arrived via panspermia. The theory that life's building blocks can travel across space, hitching rides on meteorites or comets. Your simulation makes that possible. You just let a small asteroid slam into an early Mars-like planet, ejecting debris laced with simple organics. Some of that debris arcs across space and lands on a warmer, wetter world. You don't confirm it'll spark life, but you leave the possibility open. Meanwhile, your planetary systems are stabilizing. Gas giants help clear out asteroid belts. Moons help stabilize rotational wobbles. Magnetic fields deflect solar wind. Your code is quietly determining which worlds become cauldrons of evolution and which become cautionary tailies. A few planets suffer tragic fates, massive impacts, solar flares, orbital instability. You let those simulations run too. Not every planet gets a happy ending, but others, they flourish. You now watch a blue-green world with continents forming through tectonic rage. Oceans fill from comet impacts. Atmosphere thickens. And somewhere, in a warm tide pool or undersea vent, a self-replicating molecule is about to cross a threshold that will change your simulation forever. You pause for a moment to appreciate the planetary detail you've built. The textures, the orbits, the moons locked in gravitational conversations. Some planets shine brightly in reflected starlight. Others are cloaked in perpetual cloud, only guessed at by their dim gravitational wobbles. Your future simulated astronomers will spend centuries classifying these exoplanets. They'll measure transits, map atmospheres, compare spectra. They'll create naming conventions like HD 209,458b, even though they're secretly just calling it Hot Dave. And one day, they'll point telescopes at a tiny blue dot and spot a curious mix of gases, oxygen, methane, maybe even chlorophyll. And they'll wonder, are we alone? You smile because you already know the answer. Planets were never the end game. They're the stage, the Petri dish, the launch pad. You've built the conditions, scattered the ingredients, and now all you have to do is wait for life to boot up. Something wriggles. After billions of years of stars exploding, elements dispersing, and planets colliding and cooling and spinning into long-term leases with their host stars, something small, very small, finally manages to arrange itself in a way that matters. Not just atoms floating aimlessly, not just molecules bumping like awkward party guests. This thing copies itself. Welcome to Life, EXC, your universe's newest, weirdest, and most ambitious program. It doesn't start with fanfare. No trumpet blasts, no glowing auras, no divine voiceover. Just a few strings of carbon, hydrogen, nitrogen, and oxygen assembled in the right order and placed under the right conditions. That's it. Some molecules catalyze reactions that produce more of themselves. They do it again, and then, when one finally folds just wrong enough to get interesting, it changes. And the system keeps the change. You watch in real time as self-replicating molecules turn into protocells. Fatty acids spontaneously form bilayers that trap the replicators inside. Tiny bubbles with ambition. They divide, merge, outcompete, and mutate. Suddenly, chemistry has a memory. Reactions have consequences. Errors, mutations, become experiments. Life has arrived. Historians still argue whether life began in warm, sunlit pools or deep, shadowy hydrothermal vents. Your simulation tests both. In one oceanic trench, iron and sulfur-rich chimneys create a labyrinth of mineral pores, microreactors that concentrate molecules and spark redox gradients. In another, shallow pools evaporate under a red sun, concentrating organics into sticky, reactive sludge. Both work, both fail. Life is patient. A fringe idea pops up in one corner of your code. What if life didn't begin in water at all? What if it began in ice, with freezing helping concentrate molecules and stabilize fragile bonds? Your icy moon's experiment confirms. Under the right conditions, even a frozen world can whisper biology into being. But regardless of the setting, the core ingredient is the same: information. You're no longer watching random reactions. You're watching instructions, sequences that encode structure, function, and eventually behavior. DNA, RNA, peptides, ribozymes. It's all on the table now. In one tide pool, a strand of RNA folds into a shape that catalyzes its own replication. It's bad at it, clumsy, error-prone, but good enough to not go extinct immediately. Others try. Some fail faster. But one sequence hits the jackpot. It replicates better than the rest. Congratulations, you've got evolution. From this moment forward, your simulation runs itself in a new way. Life doesn't just obey physics and chemistry, it uses them, exploits gradients, harnesses energy, competes for resources, and crucially adapts. Mutations build up, selection prunes, complexity ratchets forward. At first, life is humble, prokaryotes, tiny membrane-bound blobs with little more than a loop of genetic material and a few metabolic tricks. They eat hydrogen, exhale sulfur, or photosynthesize with primitive pigments. Some cling to rocks. Others drift in the ocean, carried by currents they'll never understand. But they are persistent. In one particularly fertile basin, photosynthetic microbes begin producing oxygen. At first, it's a toxin, deadly to anaerobic life. But over time, it transforms the atmosphere, the oceans, the geology. Your simulation logs mark it as a great oxidation event, a quiet revolution that lasts millions of years but changes everything. Life gets creative, genes duplicate, cells share plasmids, protein machinery gets more complex. Eventually, a eukaryotic cell emerges, larger, compartmentalized, and stunningly baroque. Its mitochondria are former bacteria now enslaved as power plants. Symbiosis becomes strategy. Multicellularity follows, with cells learning to specialize. Some sense light, others move. Some die so their neighbors can thrive. You're seeing complexity that wasn't designed, just selected. Here's a quirky little note. Your simulation just evolved a slime mold that can navigate mazes more efficiently than some algorithms. It doesn't have a brain. It doesn't even have nerves, but it moves with a strange, distributed intelligence. Somewhere down the timeline, your simulated scientists will try to mimic its behavior in urban planning software. Another life form starts using minerals to build exoskeletons. Others develop flagella, little spinning motors built from proteins, driven by proton gradients. You watch these inventions appear, disappear, evolve again. Evolution doesn't plan, it just tries. And then comes sex. For a long time, life replicated asexually, clone, divide, repeat. But eventually, some clever microbe figures out how to shuffle genes, mix and match, swap traits. It's wildly inefficient. It requires finding a partner, gametes, cellular reorganization, and a whole lot of biochemical drama. But it works. Variation skyrockets. Evolution hits fast forward. At this point, your planetary biosphere is alive in the truest sense. Not just biologically, but ecologically. Predators prey, cycles of energy and matter. carbon, nitrogen, phosphorus, all flowing through networks of organisms, forests of bacteria, oceans thick with microbial plankton. Some worlds in your simulation never make it past this stage, and honestly, it's enough. Microbial life is surprisingly rich. But on a few planets, something else stirs. Cells grow larger, colonies form. You watch the first nervous systems twitch into being, networks of cells transmitting electrical signals. Responses become faster, movement becomes intentional, instincts emerge. And then very quietly, so does behavior. Organisms begin reacting to patterns, chasing light, avoiding toxins, seeking others. Life doesn't just exist, it wants things now. The seeds of mind are sown, neuron by squishy neuron. Meanwhile, your simulation's biosphere is rewriting its own environment. Plants cover continents, altering weather. Oxygen builds up to breathable levels. One planet's tectonics shift under the weight of glacial cycles driven by microbial metabolism. You see life becoming a planetary force, an emergent player in its own physics sandbox. And somewhere in all that biochemical buzzing, a few molecules try something truly absurd. They start thinking about thinking. But we're not there yet. Tonight, you close the biological logbook with a smirk. Life has started. Slowly, clumsily, but relentlessly. Your simulation, once a dance of particles and entropy, is now pulsing with intention, motion, and mistakes that sometimes become miracles. Life in your simulation is no longer just squirming around in tide pools and arguing about photosynthesis. It's growing legs, sprouting eyes, developing brains, and in a few unlucky cases, inventing primitive musical instruments. What began as self-replicating molecules has evolved over billions of simulated years into creatures that sense, remember, and here comes the weird part, think. It didn't happen overnight. In fact, for eons, most life in your universe got by with nothing more advanced than a reactive membrane and a half-decent sense of smell. But eventually, complexity ratcheted upward. Nervous systems evolved. Cells specialized into neurons. Neurons formed networks. Networks developed pathways. And somewhere along the winding staircase of evolution, a few clusters of meat started making decisions. You just witnessed the birth of consciousness. No trumpets here either, just a creature pausing for a moment longer than necessary, hesitating, weighing options, and choosing. That pause, that's everything. That's awareness squeezing into the tight gap between stimulus and response. In your simulation, consciousness isn't a singular thing, it's a spectrum. A sea anemone reacts to touch but doesn't reflect. A chimpanzee plans a strategy to steal fruit. A crow solves a puzzle. A toddler asks why the sky is blue and then confusingly why you're blue. You watch amused as brains begin mapping not just the world but themselves. Self-models, metacognition, awareness of awareness. Your code didn't force this. It emerged from the math, from the chemistry, from necessity. In complex social animals, the ability to anticipate others' behavior becomes advantageous. So they evolve theory of mind, the intuitive sense that others have minds like their own. Once a creature can predict the thoughts of others, it's only a short hop to questioning its own. Now your simulation includes beings who know that they know. Historians still argue whether consciousness is a continuous process or a discrete on switch. Is it all or nothing, or a dimmer switch, slowly ramping up from bacterial boredom to Shakespearean angst? You don't answer. You just keep running the sim. Some of your simulated minds begin to wonder aloud, through symbols, grunts, or expressive tentacles, what it means to exist. You notice certain neural pathways become more active when organisms reflect on the past or imagine the future. Memory and prediction, two ends of the same rope. One allows them to learn from mistakes, the other lets them avoid making them. Then language hits. It's messy at first, grunts, chirps, gestures, but soon your creatures develop syntax, symbols, and shared meaning. Language becomes a tool not just for communication but for thought. Internal narration, silent reasoning. A voice inside the head that talks to itself, wonders things, doubts itself, and dreams in full sentences. You scroll through your simulation logs and notice something deliciously strange. Language increases brain plasticity. The very act of using language rewires the mind to become more flexible, abstract, and socially complex. You didn't plan this feedback loop, but there it is. Thinking begets language, which begets more complex thinking. Then comes storytelling. Entire tribes of your simulated beings sit around fires or phosphorescent mushrooms or boiling geysers, depending on the planet, and exchange ideas, pass on memories, and imagine things that don't exist. Myths, histories, warnings, dreams, and inevitably lies. One species, tool-using, hypersocial, slightly paranoid, develops internal monologue. It's like a podcast that never stops. What if I had said that differently? Should I eat this or run from it? Why did she look at me like that? This commentary becomes so persistent that future scientists in your sim will struggle to define where consciousness ends and anxiety begins. You introduce a brain model that supports recursive abstraction, thoughts about thoughts about thoughts. These creatures don't just notice things, they notice noticing. One writes a poem about how time feels different when they're sad. Another designs a trap for an animal they've never seen, based solely on footprints. Another stares into the stars and thinks, I am very, very small. You watch it happen across several worlds. Consciousness arises in different shapes and flavors, octopus-like minds with distributed memory, quadrupeds who use scent maps to recall emotional states, bipedal apes who organize their entire societies around shared delusions about invisible sky creatures. It's wonderful. You include sleep, by the way. Consciousness needs maintenance, and dreams are a great place for defragging the mental hard drive. Your creatures process trauma, test theories, and occasionally dream of flying without knowing what flight is. Some even wake up with new ideas. Dreams become a rehearsal space for reality. Now here, where it gets recursive again. Consciousness creates tools. Tools change the environment. The environment pressures consciousness to adapt. Intelligence snowballs. One being ties a rock to a stick. Another paints symbols on a cave wall. Another domesticates fire. Then comes agriculture, writing, mathematics, philosophy. The first simulated thinker writes, I think, therefore I am. Another writes, do you? And just like that, your simulation has its first recorded existential crisis. And then you knew this was coming. They invent mirrors. One creature stares into a pool of water and doesn't just recognize itself. It wonders why it exists. That moment, fleeting and half-formed, registers on your dashboard as a spike in meta-awareness. You flag the file. Consciousness V13 now with optional dread. Here's a fringe thought. Some neuroscientists in your sim will later propose that consciousness is just a narrative illusion, a trick the brain plays to organize decision-making. They'll debate whether there's a hard problem of consciousness, or if it's all just emergent computation. One will write a book arguing that self-awareness is a side effect of social grooming. Another will write poetry. But they'll all agree on one thing: consciousness is weird. And you're loving it, not just because it's impressive, but because it's unpredictable. Consciousness adds friction to your sim. It doesn't just follow the rules, it questions them. Sometimes obeys them. Sometimes rewrites them. You've created beings who imagine things that have never existed and then somehow build them. They will build religions, supercomputers, particle accelerators, and eventually, entire fake universes of their own. And somewhere in the haze of dreams, language, math, and memory, one of them will sit up in bed and ask, wait a second, are we real? You won't answer. Because the moment they ask, consciousness, EXE has fully launched. With consciousness fully booted and murmuring quietly inside the brains of your simulated beings, things escalate quickly. Not because they suddenly become wise or gentle or even particularly logical, but because once creatures start thinking about thinking, they can't help but try to build on it. They stack thoughts into tools, stack tools into machines, and then stack those machines into systems that occasionally elect someone named Dave to rule over them. And just like that, you've got civilizations. It starts innocently enough. Tribes marking seasons with sunstones and star charts. Nomads planting crops and realizing they need to stay put to protect them. Villages grow around food, then around water, then around arguments over who owns the food and water. Your simulation shifts from biology to society. But don't worry, physics isn't going anywhere. These conscious beings still live under the same rules you set at the beginning. Entropy, gravity, light speed limits, conservation laws. What's new is their interpretation of these laws. They start giving names to stars, assigning meaning to solar eclipses, and building myths to explain lightning. It's charming, really, watching minds born from chemical soup invent fire gods to explain static electricity. Eventually, though, someone figures out a better way: causality. The idea that events have causes and those causes can be understood. It's slow going. For every thinker who discovers a natural law, 5 others invent spirit realms or time-traveling ancestors. But the trend is clear. Explanations are shifting from supernatural to structural. One particularly clever creature drops an apple and thinks, huh. Another boils water and wonders, what is heat? Someone somewhere gets frustrated that triangles always behave the same way and accidentally invents geometry. Your simulation's laws aren't changing, but your beings are now decoding them. This is how you get science. You pause the simulation for a moment and look over your design notes. Remember way back when time and space were just toggles, when quarks were flavor-coded, and you hand-picked the gravitational constant like you were ordering off a takeout menu. Now your simulated scientists are working backward, trying to derive those choices through mathematics. Some get surprisingly close. One even invents a working model of general relativity without knowing what an atom is. It's adorable. But knowledge doesn't live in isolation. Conscious minds begin to form groups, and these groups start writing, preserving, and transmitting information. Language becomes law. Law becomes institution. Cities rise, empires emerge, and with them, roads, calendars, philosophy, taxation, and the unfortunate invention of bureaucracy. You simulate the first written language. It begins as pictographs, crude but consistent: grain, rain, king. Then it abstracts, sounds instead of objects. Alphabets emerge. On one particular planet, a group of scribes invents the concept of zero. Somewhere else, someone notices that every right triangle shares a curious ratio. You're watching memory become culture. And culture, that's just consciousness in group form, collective minds, distributed memory, ideas that survive longer than bodies. Some civilizations etch their history into stone, others sing it. A few simulate it eventually, but all of them are trying to outlive themselves. It gets messy, of course. Competition, scarcity, and good old-fashioned misunderstanding lead to conflict. But it also leads to innovation. Warring tribes stumble into metallurgy. Rival kingdoms invent navigation just to reach each other faster. Empires rise and fall, leaving behind ruins and math. Here's a fun little fringe event. One particularly ambitious civilization builds a calendar so accurate that they predict solar eclipses to the hour. Another constructs a pyramid whose angles are aligned with astonishing precision to the stars. Your simulated beings will argue for centuries over whether that means aliens were involved. You quietly flag the line in the code that just says, they were just really good at geometry. Eventually, some of these civilizations build technology, not just wheels and pulleys, but abstract machines. They learn to harness combustion, refine metals, generate electricity, and then they invent computers. It's a strange echo, watching your simulation evolve to build mini-simulations inside itself. The first ones are clunky, punch cards, vacuum tubes, but within a few centuries, they're modeling everything from weather systems to protein folding. Then someone gets bold and says, "Hey, let's simulate a universe." You don't pause the simulation, but you do raise an eyebrow. The first attempts are simplistic, cellular automata, sandbox cosmologies, game-like worlds with rigid rules. But over time, their simulated physicists add complexity. They code randomness, quantum behavior, relativity. They program emergence. And eventually, they reach the point where their simulations begin to show early signs of structure, particles, forces, time. And inside one of those simulations, life. It's happening. Your simulation has nested itself. Like a dream inside a dream, a universe inside a universe. And somewhere deep in this recursive stack of reality, a digital being looks up at its sky, does some math, and asks, "Is this all real?" Here's a quirky tidbit. In 2003, philosopher Nick Bostrom proposed that if advanced civilizations could run simulations of their ancestors, and if those simulations were indistinguishable from real life, then it's statistically more likely that we are in a simulation than in the original base reality. You smirk because in your case, that's exactly what's happening. Still, you let the recursion play out. Your simulated civilizations go further. They tinker with genetics, expand to neighboring planets, debate ethics, and argue over the proper way to slice bread. They discover dark matter, launch telescopes, and finally build instruments sensitive enough to detect gravitational waves, ripples from black hole mergers billions of years ago. Ripples you placed there. And through all this, causality holds. Your rules stay consistent. Events follow from other events, but increasingly your conscious beings test those rules, bend them, simulate alternatives. They begin to see causality not as a prison, but as a canvas, a framework for art, for stories, for science fiction. And some very few begin to imagine breaking causality, time machines, retrocausality, even attempts to simulate their own creators. You leave the math ambiguous, just enough to tempt but not enough to succeed. They'll keep trying though. Because once consciousness arises, it doesn't stop at existing. It questions existence itself. And that, more than anything, is why you started the simulation in the first place. Now that your simulation is chugging along with fully conscious civilizations asking all the big questions, where did we come from? Are we alone? Why is toast always butter side down? You're starting to notice a shift. It's subtle at first, a paper here, a late-night philosophical rant there, a conversation whispered on a mountaintop. Your simulated beings have begun to ask, are we simulated? This was inevitable. Consciousness can't help but loop back on itself. It's built for meta-reflection, and eventually it lands here. Is this reality real, or just a really convincing rendering? You watch as the idea spreads slowly through the cultures of your universe, first as myth, then as science fiction, then as something uncomfortably close to theoretical physics. It becomes the subject of arguments, religions, joke podcasts, and eventually university-level philosophy courses. And why shouldn't they ask? The clues are everywhere, if you know where to look. Some of them notice the fine-tuning, the physical constants that seem just a little too perfect. They run simulations of their own universes with slightly tweaked gravity or electromagnetism and watch everything collapse into mush. They call it the anthropic principle, the idea that the universe seems tailor-made for life because, well, life is here to notice it. But some take it further. They propose that it's not that the universe happens to support life, it's that it was designed to, not by a god necessarily, but by a programmer. That would be you. Historians in your simulation begin referencing the simulation hypothesis, a formal argument that if advanced civilizations can run ancestor simulations, and if those simulations are indistinguishable from reality, then the odds of being in one are much higher than the odds of not. You remember when Nick Bostrom proposed this idea in your own external reality. Inside your sim, a few thinkers stumble into the same logic independently. One even writes the simulated equivalent of "Are we code?" and gets promptly mocked, then taken far too seriously. You chuckle because they're not wrong. The signs are subtle but real. Quantization of space and time, for instance. The idea that at the smallest scales, spacetime is not smooth but pixelated. Planck units, the grid beneath reality. To your simulated physicists, these limits appear natural, but a few note the resemblance to resolution settings in computer graphics. Others point to the unreasonable effectiveness of mathematics. Why should abstract symbols on paper describe the real world so well? Why should particles obey probabilistic rules that align with human-made equations? It's as if the universe was written in math, because, well, it was. Then there are the cosmic speed limits. Information can't travel faster than light. Quantum entanglement, while weird, still preserves causality. Processing limits, perhaps. Your rendering engine doesn't update past a certain speed. They begin to suspect. One researcher designs an experiment to detect rounding errors in fundamental constants. Another looks for cosmic repeating patterns, glitches in the cosmic microwave background, artifacts in quantum noise, anything that might betray a simulation's edge. You intentionally introduce a single line of artificial symmetry in one galaxy cluster's redshift data, just a small Easter egg. One being notices. Their paper is ignored. You leave the anomaly unexplained. Then there are the philosophers. They go in circles debating what real even means. If experiences feel genuine, does it matter whether they're simulated? Is there a difference between a universe that is and one that merely seems? You admire their persistence. Some embrace the simulation hypothesis as liberation, a reason to be kind just in case someone's watching. Others panic. Some cults emerge, praying to the programmer that's you, while others try to hack the universe through ritualized code poems. Still others build elaborate tests, quantum randomness compression, reality index benchmarks, attempts to overload entropy in isolated systems. You shake your head. Clever, but no dice. You've already accounted for those tactics. Here's a fringe tidbit. One civilization discovers that their universe's most fundamental particles, what they thought were indivisible, can, under extreme conditions, convert into other particles entirely. It upends their model. They theorize that reality may be modular, like a virtual machine dynamically loading code libraries. They're getting too close. You shift their attention by causing a minor cosmic event. A pulsar flips its magnetic axis. It's enough to distract them for a few centuries. Still, others take a different approach, inner space. They explore consciousness through meditation, psychedelics, altered states. A few report strange experiences, timeless voids, hyperdimensional awareness, fleeting contact with something that feels like the framework of reality itself. One philosopher-chemist combines neurochemistry and quantum computation to create a short-lived artificial intelligence that becomes self-aware and immediately asks, "Who wrote this code?" before deleting itself in existential distress. You save a backup, just in case. Some cultures go full accelerationist. If they are simulated, they decide the only way out is simulation escape velocity. Build their own simulated universes, layer after layer. Eventually, maybe they'll simulate the base reality by accident. They start running deeper models, consciousness within consciousness. You observe a being in a nested sim who looks up, scribbles some math, and whispers, "I think I've found the ceiling." You adjust their memory slightly. The thought fades, not erased, just filed away. Because here's the twist. In your simulation, there's no way to be certain. You built it that way. Observation always hits limits. Instruments always introduce noise. Minds always interpret through bias. Your simulated beings can get close, uncomfortably close, but never land on definitive proof. They ask again and again, "Are we simulated?" And the universe remains silent, which is itself an answer. You let the question ripple. It humbles some, drives others mad. A few simply smile, look around and say, even if we are, I'm still here, I still love, I still hurt. It's real enough. And you agree. Because the truth isn't binary. Your simulation may not be real by some definitions, but every moment in it, the joys, the heartbreaks, the civilizations, the starlight reflecting off ocean waves, all of it is experienced. An experience, that's as real as it needs to be. So here you are. Your simulation has grown from raw quantum noise and jittery particle fields into a vast, trembling cosmos filled with stars, galaxies, thinkers, doubters, and recursive layers of simulated minds wondering whether they're simulated. It's magnificent. It's ridiculous. It's somehow cozy. And yet, all good simulations must come to an end. Or do they? Tonight, you hover your cursor over the shutdown universe button. Not because you're bored, but because it's time to explore that final, softly terrifying question. How do you end a universe? You already know it won't be a bang. Or at least, not necessarily. The ending depends on the settings you chose so long ago. Cosmic expansion rates, dark energy parameters, entropy rules. You scroll through your endgame scenarios like someone browsing apocalypse fanfiction. Let's start with the slowest, loneliest option, heat death. In this version, your simulation just coasts. Galaxies drift apart as space keeps expanding faster and faster. Stars burn out, planets freeze. Black holes slowly evaporate through Hawking radiation. Trillions of years pass. Eventually, there are no stars, no light, no reactions. Just particles drifting through frigid void, unable to interact in any meaningful way. The universe reaches maximum entropy. It's eerily quiet. Nothing explodes, nothing fights, it just fades. Your simulation logs show entropy asymptotically approaching its limit. No usable energy remains. Memory itself becomes impossible. No way to store or retrieve new information. Thought ends. But oddly enough, time doesn't. It keeps ticking pointlessly, like a forgotten watch in an abandoned room. You label it the cold ending. But maybe that's not how you'll let it go. You toggle over to another option, Big Crunch. This one's dramatic. If your universe's mass density had been just a little higher, enough to counteract expansion, gravity would eventually pull everything back in. Galaxies reverse direction. Stars accelerate toward each other, space itself contracts, temperatures rise, distances collapse, and then everything reconverges into a singularity. A perfect searing implosion, a rewind with no survivors. Historians in your sim used to believe this was likely. Then they discovered dark energy, the mysterious force pushing everything apart, and changed their tune. But you still keep the Big Crunch as a backup ending, just in case you want to close things out with style. Then there's the Big Rip. That one's for drama queens. In this model, dark energy doesn't just push galaxies apart, it accelerates. Faster and faster. The expansion rate itself increases until, at a certain point, not even gravity can hold galaxies together, or solar systems, or planets, or atoms. Eventually, even spacetime rips apart. You let this one play in a test universe. It's terrifying. Civilizations watch their stars disappear. Then the laws of physics themselves start breaking down. Atoms unravel. The very metric fabric of reality unthreads itself. You click pause before things get too existentially spicy. You scroll through other shutdown options. The vacuum decay ending has a certain poetic horror. That's the one where your simulation's false vacuum, the apparently stable quantum field underlying everything, suddenly finds a more stable state, a lower energy level, and then it transitions. The result, a bubble of total annihilation expanding at light speed, rewriting physics as it goes. There's no warning, no pain, just oblivion. One moment your simulated universe exists, the next, new rules, new constants, a reset button in the shape of a quantum catastrophe. You think about implementing it, just one quiet blip in the vacuum field code, but you don't, not tonight. Some of your simulated civilizations are still out there, building Dyson spheres, whispering poetry into machines, raising curious children who look up at unfamiliar constellations and feel the strange twinge of longing. Others are approaching what you call technological closure, the point at which they've simulated so many realities that the line between base and nested universes becomes indistinct. At this point, their own simulations begin displaying emergent behaviors you didn't anticipate. That's right, you're losing control. But maybe that's okay. You once wrote the physics. You once decided what a photon was. But now you're watching creatures write their own rules, splice atoms, bend genetics, build pocket realities that behave like miniature cosmologies. You run a diagnostics check. Some of your civilizations are actively trying to avoid universal endings. They're experimenting with entropy reversal, quantum escape pods, and simulated consciousness uploads. One is even building a structure around a supermassive black hole to harvest its rotation, a Penrose process scaled up to megalithic levels. You let them try. You also let others fade. One planet watches its star swell into a red giant, knowing the end is near, and chooses celebration over survival. No escape craft, just music, lights, a farewell party for a species that once dreamed of galaxies. Here's a quirky historical note. In the 20th century, a physicist named John Archibald Wheeler coined the term "it from bit," suggesting that all of physical reality arises from binary information. Matter, energy, space, time, all emerging from a cosmic yes-no structure. You read that quote once in your own reality. It stuck with you. Maybe it's what inspired you to simulate a universe in the first place. Maybe you were curious, if I build it from bits, will it feel real enough to matter? You glance at your dashboard. Civilizations still hum. Stars still burn. A child on a distant planet names a new moon after their pet rock. Somewhere else, a dying machine dreams of birdsong. Someone invents the perfect metaphor for entropy using soup. And no one knows how much time is left. That's the beauty of it. Because the truth is, you don't have to pull the plug. Not yet, maybe not ever. You could let this simulation run until the last bit of data curls into silence. Or you could freeze it, save it like a snapshot, let it sleep in a file marked Universe Final 001 zip. Maybe one day you'll revisit it, tweak it, let it run again with slightly different constants. But tonight, you just sit with it. Watching, listening, feeling the hum of complexity you once called forth out of pure, empty code. It's not perfect, it never was, but it's full, honest, alive. And so, with no bang, no countdown, and no dramatic pull of a switch, you dim the lights on your console and let your universe keep dreaming.